And now, let us prove that this is S n is. So, claim we want to show S n is increasing. So, let us fix x belonging to x to show S n plus 1 of x is bigger than or equal to S of x, S n of x for every n, right. So, let us look at that. So, why is that true? Now, look what is the value of. So, either f of x is bigger than or equal to n plus 1 is no, let us look at slightly differently. So, I want to prove that S n is increasing. Okay. So, to prove the increasing part, so let us fix n, right. So, we want to look at, so what is S n plus 1 of x. So, that is going to be dependent upon whether, so either it is n plus 1 or it is going to be some k minus 1 over 2 to the power n plus 1 for some k between 1 and n plus 1 times 1 over 2 to the power n plus 1. So, what we are saying is S n plus 1 x, either it will be bigger, it will be equal to n plus 1, that will be the case if f of x is bigger than or equal to n plus 1, or it will be equal to one of lower values of one of the sub intervals at the n plus 1th stage. In the n plus 1th stage, we will be dividing the interval into 2 n plus 1 parts. So, let me write this, draw this picture slightly here to understand what is happening. So, here is, so this is, here is, let us say j by j minus 1 by 2 to the power n, and that is j to the power 2 to the power n. At the nth stage, right, f of x is somewhere in between. Okay. Now, at the next stage, what we are doing? We are going to divide this into 2 equal intervals. So, that this part is something divided by 2 to the power n plus 1, and this part is something divided by 2 to the power. So, what will be this? So, this will be 2 times j minus 1 divided by 2 to the power n plus 1, okay, and this part would be 2 j divided by 2 to the power n plus 1, okay, and that is a middle line in between. So, now my S n plus 1 x, okay, depending on f x, if f of x is here, if this is f of x, then S n plus 1 is, this is the value of S n plus 1. So, this is the value of S n plus 1, and if f is here, then this is the value of S n plus 1. So, either f of x will be here or it will be here. Okay. So, if f of x is here, it lies in that interval of length 2 to the power n plus 1, the value is a lower end point. So, value of S n is here. Okay. But in that case, what is the value of this is the value of S n plus 1. So, this is the value of S n plus 1 x, and what is the value of S n? That is always going to be equal to this value. Okay. And if f of x is this, then this is the value of. So, S n plus 1 x either it will be here or it will be here, and S n plus 1 of x will always be here. So, this value is less than or equal to this value. So, that analysis let us just write. So, it is equal to this. So, in either case, so S n plus 1 of x, either it will be n plus 1. So, either it will be n plus 1 or it will be which is bigger than n, which is equal to S n of x. If not, if it is below, right, then the value is if it is in one of those intervals, then the value is going to be some k minus 1 over 2 to the power n plus 1, right, which is always going to be equal to 2 to the power n, the lower value here. So, let us it is difficult to write those symbols. So, that lower value this k minus 1. So, this is k minus 1. So, that is less than or equal to j minus for some j, and that will be equal to j minus 1 over 2 to the power n, which will be equal to S n of x. Geometrically, it is quite clear what is happening. So, either if f of x is here, in between here, then the value of S n plus 1 is this value, and if f of x is here, S n plus 1 is this value, which is the value of S n also. So, in either case, so this implies hence S n x is increasing. And let us prove that S n x converges to f of x, that the limit is equal to f of x. So, if we fix x, if x is fixed, so then either f of x is equal to plus infinity, that is one possibility, but then if this is plus infinity, what is S n of x? That is always f of x is always bigger than n for any n. So, S n x is going to be equal to n, which goes to plus infinity as n goes to infinity. So, if f of x is plus infinity, then S n x is equal to n for every n, and hence it goes to plus infinity. Or what is the second possibility? F of x is not infinity, that means it is a real number. So, it will lie between some n, it will be less than or equal to less than or equal to some n. So, it will be some 0 less than or equal to n. So, then in that case, so there exists a n such that this is happening. Okay. So, that also will be less than n plus 1 and so on. So, and what is S n of x in that case? In that case, S n of x is going to be some k minus 1 over 2 to the power n, right. If this is less than this, then f of x will belong to one of the intervals k minus 1 over 2 to the power n and k by 2 to the power n, right. So, implying that is the same. So, what is the difference between S n and this? S n is the lower value, f is something in between. So, that implies that the absolute value of f of x, or actually f of x is bigger. So, minus S n of x will be less than k minus 1 by 2 to the power n, okay, for some n. And that means, if this is happening for some n, so let us say for some n naught, then for every n bigger than or equal to n naught, okay, f of x minus S n of x is less than, right, it will be less than those k minus 1 by 2 to the power n for some k and some n. So, it will be less than not k minus 1 over 2 to the power, the difference will be at the most. Both lie in the interval of length 2 to the power n naught. So, it will be less than 1 over 2 to the power n 2 to the power n for every n bigger than n naught, and that implies that S n x converges to f of x. So, let me just go over to the construction once again to understand, because this is a important construction. So, it says that I want to, given a function f which is non-negative measurable, we want to construct a sequence of simple functions which are non-negative, which are increasing, and they converge to f of x. So, what we do? We divide the range. So, this is the range of the function, is a subset of it. So, we divide it into a partition the range. So, partition into 0 to n. So, this is 0 and this is n union n to infinity upwards. So, this is, and the portion 0 to n is divided into sub intervals each of length 1 over 2 to the power n. So, this will look like k minus 1 by 2 to the power n, k by 2 to the power n, k equal to 1 from 1 to how many such intervals will be there? Each of length 2 to the power n, total length is n. So, n times 2 to the power n. right. So, this is we have partitioned range. Now, given a point x, f of x, either it will be beyond n, or given an n, either it will be beyond n or it will be between 0 to n. If it is beyond, then we define S n of x to be equal to n. So, if the value of f of x is bigger than n, then we define it to be equal to n, and if it is not, then it will be between the interval 0 to n. So, it will fall into one of the sub intervals, say somewhere here in some k minus 1 by 2 to the power n to k by 2 to the power n. So, we define that lower value of that interval, that is k minus. So, this is k and this is k minus 1. So, the lower value to be equal to the value of the function S n x. So, this sequence is increasing. See, for any point x, f of x and S n will be at the most a difference of 1 over 2 to the power n, right, for n large enough, or if not, then S n will go to infinity. So, that is the idea that it converges, and increasing once again comes from the fact that we are taking the lower value at every stage. So, at any stage, either S n plus 1 is bigger than n plus 1, in that case it will be bigger than n also. So, S n plus 1 will be bigger than S n. If not, it will be in one of those sub intervals or length 2 to the power n plus 1, but how did we get those? So, that is, so this total length is 1 over 2 to the power n. So, when we want to divide the next stage from S n to S n plus 1, we divide it into two equal parts. So, if f of x is here, then S n plus 1 is the lower value here, or if S n plus 1 is here, it is a lower value. So, in either case S n is always going to be the lower value. So, that says it is increasing and convergent. So, that proves the theorem that. So, what we have shown is the following: given a function f x to 0 to plus infinity measurable, there exists a sequence S n of non-negative functions which are simple and measurable increasing to f. So, that is what we have proved. So, let us come back to the theorem which said that this is one of the key theorems in the notion of for the concept of measurable functions, that every non-negative measurable function can be approximated, can be obtained as a limit of non-negative simple measurable functions, and these non-negative simple functions can be selected to be a increasing sequence. So, you can approximate a non-negative function as a limit of increasing sequence of non-negative simple measurable functions. So, this immediately gives us a corollary for functions which are not non-negative, but let us before that let me just observe that this in the proof, if the function f is bounded, then the sequence can be chosen to be S n to be uniformly increasing to f. Not only it converges pointwise to f, you can actually claim that it converges to f uniformly. So, to prove that it converges to f uniformly, if we just observe, because the function is bounded. So, let us just observe that if the function is bounded, that means what? That means f is a bounded function. So, its graph. So, there is going to be n. So, that the graph of the function always stays below this, right. So, once n is fixed, that means f of x is always going to belong to 0 to n for some n, and for that f of x, right. So, let us say n naught. So, n naught is the bound for the function. So, then f n x minus S n of x is going to be less than 1 over 2 to the power n naught for every n bigger than n naught. So, this works for all. Okay. So, given epsilon bigger than 0, I can select n naught such that this is true. That means, the same epsilon works for every x. That means, the sequence S n converges uniformly to f of x. So, this is an observation which we may not be needing it, but it is good to observe that if f is a bounded measurable function, So, this theorem says that if f is a bounded measurable function which is non-negative, then there is a increasing sequence of non-negative simple functions uniformly increasing to f. So, this is the case for when the function is non-negative. In the general case, for a general measurable function, we can look at the positive part and the negative part of the function, approximate the positive part by a sequence, approximate the negative part by a sequence of simple functions, and then look at the difference of the two, and that will give us a sequence of simple measurable functions converging to f. They will not any longer be monotone. So, as a consequence, we have that if f is not necessarily a non-negative function, if f is a measurable function, right, then there exists a sequence of simple functions converging to it. So, what we are saying is, if f is measurable, then I can write f is equal to f plus minus f minus f minus, and we just now observed f measurable implies both of them are measurable, and for this there is a sequence S n which is increasing to of simple measurable functions non-negative increasing to this. There is a sequence, another sequence, call it as say S n dash, which is again non-negative simple measurable functions increasing to f dash. So, if I look at this plus this, okay, then that this minus then this will converge to f. So, call this as your new sequence. So, this is call it as phi n. So, phi n is a sequence of, because difference of simple measurable functions is measurable. So, this is a S n is is a simple measurable function, S n dash is a simple measurable function. So, phi n is a simple measurable function. S n converges to f plus, S n dash converges to f minus. So, the difference will converge to the difference which is f. Only thing is, so this phi n's converge to f, but we cannot say phi n's are increasing anymore. This each one of them is increasing, but the difference may not be increasing. So, that proves that for a general measurable function is measurable if and only if there is a sequence of simple measurable functions converging to f. So, now let us look at some more general properties of measurable functions. Let us take, so we are going to look at the various properties given two functions f and g which are measurable, given a scalar, whether sum of the measurable functions is measurable or not, whether the product of measurable functions is measurable or not, whether scalar multiple of a measurable function is measurable or not. So, let us list all the properties which are true. So, first says if f is measurable and alpha is a scalar, then alpha times f is also a measurable function. So, for that this alpha could actually be any extended real number also, depending upon because we are taking only. So, keep in mind I am taking only real valued functions for the time being. F and g are both real valued functions which are measurable, and alpha is a real number. So, the claim is alpha f, which is again a real valued function, is measurable. Now, we can, for this we can apply our sequential criteria, because f is measurable. So, there is a sequence of simple measurable functions converging to it, and so look at the sequence. So, let us look at the proof of this. So, that says f measurable implies there exists a sequence S n of simple measurable functions converging to f, but that implies by the properties of sequences alpha S n converges to f. Because S n is simple measurable, a constant times a simple measurable function is again a measurable. So, this is a sequence of simple measurable functions converging to f. So, implies by the previous theorem f is measurable. And the same proof works for sum of two functions. Let us say f and g are two measurable functions. We want to prove that f plus g is measurable. So, f measurable implies there is a sequence S n of simple measurable functions converging to it. G is measurable. So, there is a sequence S n dash of simple measurable functions converging to it. So, that implies that S n plus S n dash converges to f plus g. And this is once again this is a sum of simple for every n, this is a sum of simple from measurable functions. So, this is again a simple measurable function. So, we got a sequence of simple measurable functions which converges to f plus g. So, implies that f plus g is measurable. Okay. So, that implies f plus. So, we have proved the next step, namely if f and g are measurable, then f plus g is also measurable. Let us look at the next property. If f is measurable, then mod f is also measurable. Why is mod f measurable? You can look at two different ways. Now, we have got enough techniques to conclude this. See, either we can write mod f is equal to f plus plus f minus. This is a observation which will play a role later on also. This is the positive part of the function, this is the negative part of the function. F measurable implies both f plus f minus measurable, implies f plus plus f minus measurable, and this is precisely my f. So, that is one way of looking at it, or you can also look at from sequence point of view. F measurable implies there is a sequence S n of simple measurable functions converging to f. Okay. But then a simple argument which works for sequences, which what I have already seen, that mod of S n converges to mod f. Okay. And observation, if S n is simple, then mod f also is, mod S n is also simple for every n. So, there is a sequence of simple measurable functions converging to f, mod f, that means mod f is measurable. So, either you can look at sequences or you can look at the positive part and negative part. Either one will help you to conclude that if f is measurable, then mod f is also measurable. Let me look at another property of measurable functions, namely that if we have seen this property for simple functions, that if E is a set in the sigma algebra S and f is measurable, then product of f times indicator function of E is also a measurable function. So, once again we can take the help of the criteria just now proved. F measurable implies that there exists a sequence of simple measurable functions converging to f at every point. But once that is true, if S n converges to f, then that implies, look at chi e times S n, that will converge to chi e times f, right, because this remains multiplying by a function. So, this converges to the simple properties of sequences. And now, observe that this is, if S n is simple measurable function, then the indicator function of E times S n is also a simple measurable function. So, that converges to indicator function of E times. So, that implies that indicator function of E times f is measurable, right. In fact, we can go a step further and prove that you can multiply by the same argument, supposing f and g are measurable. For f, we have got a sequence S n of simple measurable functions converging to f. We have got a sequence S n of simple measurable functions converging to S n dash converging to g. So, that implies if I multiply S n dash, that converges to f times g. And product of simple measurable functions we have already seen is again a simple measurable function. So, a sequence of simple measurable function converging to f of g, that means implies that f g is measurable. So, product of measurable functions is also measurable. I think we will close here today. and look at the sequences of measurable functions next time. So, today what we have proved, we have looked at the an important criteria, a characterization of measurable functions. A function f defined on a set x taking extended real valued functions is measurable if and only if, keep in mind it is a characterization. So, f measurable, f a function defined on x is measurable if and only if we can find a sequence of simple functions converging to it. And if f is non-negative, we can find this sequence of simple functions S n which is increasing and converging to f. If in addition we know that f is a bounded measurable function, then you can have the sequence of simple functions S n which converges uniformly to f. So, that is the important criteria. We have seen some applications today, we will see more applications later on also. And then we looked at the algebra of measurable functions. We proved that if f is measurable, then scalar times f is also a measurable function. If f and g are measurable, then f plus g is also measurable, f into g is measurable, mod f is also measurable. This is for the real valued functions. In case the functions are extended real valued, while defining f plus g and f into g, you have to be slightly careful, because f may take the value plus infinity at a point and g may take the value minus infinity, then how will you define f plus g? So, for such kind of problematic sets, we can separate them out, right. So, separate out a set A on which f of x is plus infinity, or g of x is equal to minus infinity, or f of x is minus infinity and g of x is the plus infinity. So, on this set A, we may not be able to define what is f plus g, but outside that we can define f plus g, and this set where f is plus infinity and g is equal to minus infinity or other way around is a measurable set, is in the sigma algebra. So, we can change the values, we can define f plus g to be equal to anything we like, and still that f plus g will be a measurable function. So, modifications of the algebra of measurable functions, the properties still remain true when the functions are extended real valued. We will continue the study of sequences of measurable functions next lecture. Thank you.